So where did this ice core data come from anyway that is used in this ice core record investigation? In 2005, I attended the American Association of Physics Teachers Conference in Albuquerque, and I had a workshop there and a poster session, and in between I was looking through the catalog, the sessions, to see if there's something that I might be interested in listening to, and came across this title: Evidence for a Stratigraphic Record of Supernovae in Polar Ice. Supernovas in ice? Oh, well, that of course caught my attention immediately. That just sounded so interesting. But then the kicker was this. Underneath it was a brief description that said that in that polar ice there might be a possible dating of the Cassia supernova event. Well, this image here on the right is a Chandra image of the Cassia remnant. It is a million-second observation of Cassia. These are all X-ray energies. And see, Cassia was the calibration extended source object for the Chandra mission. So it was when those photons came down that showed us the Cassia supernova remnant. That is when the mission people knew that they had a functioning, really awesome X-ray observatory going, and everybody was so excited. So yes, we've always had this special friendship with Cassia, and it's actually the youngest one that we've been able to study, so it is observed an awful lot. But there's always been this mystery. When did the Cassia supernova event really happen? It would have been in the 1600s. There was all kinds of amateur astronomers in Great Britain, Europe, and someone should have seen the Cassia event. And there have been a couple of ideas or clues over time, but still we do not know how that happened. So I went and listened to that talk, and the presenter's name is Gisela Dreshoff, and Gisela was just absolutely stunning and fascinating. If you want a role model in science, a female role model for your female students, you cannot do better than this elegant, charming woman. She is well past retirement age, shall we say. She's still very active in doing research. She presents scientific talks all over the world at scientific conferences. I have had the honor to work with her myself, and she's come to some of my workshops to present. When I contacted her after I returned from that conference, she sent me the publication, at the time it was 415-year Greenland ice core record of solar proton events. And within that was that ice core strip that I just showed you. I cut it out and glued it together, and when I saw that ice strip, I said, wow. An educator would love to use this in the classroom, and as a student, I would absolutely love to be able to work with this material. So how can I make it logistically feasible to use this data in a classroom situation? Gisela herself, this is her on the cover of a book, The New Explorers, that was published in around 1981. She was one of the first women to work in Antarctica, and she spent 20 different times that she went into the field to do field workshop in both Antarctica and in Greenland. She worked for NASA for a long time. They were interested in the solar radiation effects on astronauts. So she worked with that program, the Apollo program, on how high energy radiation would affect the astronauts in space inside the capsule. She was doing gamma ray spectroscopy to see if the uranium deposits underneath the surface of the ice in the Arctic regions. And they even named a mountain after her. So in Antarctica, there is Mount Dreshoff. So she is a really awesome, phenomenal person. And just to keep her hand in, keep her interested, she is just on the side right now with a couple of other people writing a book on the 5-dimension space-time universe. We have produced, the EPO office has produced 2 podcasts, so you can actually listen to Gisela. The first one talks about gamma ray astronomy, solar radiation, and all of her work in the field. And the second part focuses in on CAS-A and why she thinks that that you can correlate nitrate anomalies in the ice core records with supernova events. So the teacher guide gives you a lot of suggestions for classroom logistics. This is what the actual worksheet looks like, printed out 24 by 24. If you have that printed out as a disposable, just plain paper at a Staples store, you can get away with it for about $3. And how many of those you need depends upon how you're going to use them with your students. If you're going to use, you do it individually with groups, how many people in a group. And if you decide to get them on the really heavy paper and laminated, then that is about $30 per sheet, where the plain paper and pencil is about $3 per sheet. So if you decide you're going to be using this more than once, then it would be a good investment, because then they would last forever with using non-permanent markers for the labeling. I listened to that talk in 2005. The investigation was posted in 2011 because it took 6 years to find a way to reasonably use this complex set of materials in the classroom. Fortunately, I was helped with a resource agent of mine, Pamela Perry, a physics teacher in Lewiston, at the Lewiston High School in Lewiston, Maine, who helped me out with that by using it with her students. So also, you also have to make a decision, is this an end-of-the-year project? Are you going to do the first section after you've done volcanism and plate tectonics? Do you do solar weather at all, or the Earth-Sun connection? Then you could do the second part of it then. You could leave the last part until you do the astronomy section if you teach earth science and you include astronomy in that. There are so many different ways of doing it. You can do it in chunks, you can do it all in one fell swoop, you can do it as a project for the entire class, or you can assign it as individual projects. And do not forget that you can also have them investigate the different types of history and geology that goes along with this ice core investigation also. So the heart and soul of this is obviously absolute and relative dating, which most scientific disciplines do have within their content, and the difference between instrumental and proxy data. This poster was produced by Zach Smith of the LastEnvironment.com, which shows that instrumental data goes back a few hundred years. If you want, for instance, to go further back, you can look at the pollen record in lake sediments. That will take you back to about 60,000 years. But if you want to really go back in time, ice core records and deep ocean, deep sea sediments will take you back in Earth history to about 800,000 years at the deepest point that we have found yet. So there is a difference between instrumental, direct measurements, and proxy data, which is data we get by measuring something else that we correlate to the answers that we're looking for, the data we're trying to find.